Good morning, and thank you very much for the invitation to speak today. It's great to see a great number of friends and colleagues, and always a pleasure to be back in Britain. I'm going to try to, over the next 40-odd minutes, take a different stance on what HPC traditionally has been used for. I'm going to try to move away from the notion of a single large task which hopefully runs on all of your HPC system, and start thinking about workflows. And workflows mean many different things to many different people. So I'll spend about 5-10 minutes trying to give some examples of workflows so as to level set what we're thinking about. But if there's nothing else you take from this talk, the one or two things I'd like you to really think, to appreciate, in spite of going through the next 40 minutes, hopefully you'll get the details, but the few things, the high-level points I'd like you to appreciate are, A, we have to rethink what performance means in the exascale and post-exascale era, and thinking about just computational performance, as in what your scaling is on a large number of nodes, is not going to be the same as scientific discovery. That's not going to be the best indicator of scientific discovery. And the second thing I want you to appreciate is the fact that slowly but steadily, as we start thinking of the machines coming in after the first set of exascale machines, workflows are being privileged as first-class entities on these systems that are being designed. And the consequences, the implications there are truly important and worth taking a few minutes to discuss and think about. And so that's really the kind of my talk. Two parts: try to motivate everybody, bring us all onto the same page, to say workflows are the new applications, for reasons hopefully I'll spend some time on, but then really think quite deeply a bit about, so what are the implications? And there'll be a small interlude in between where I'll expose some of my biases of specific kind of workflows, namely AI-coupled workflows. So that's the kind of agenda for the next 35-40 minutes. There'll be some surprises for me because slides that I sent in the morning, I realized the animations don't work, and therefore I changed some of the ordering, but that didn't show up here. So we'll see how that goes. Some uncertainty is always good early in the morning. Okay, so I don't think I need to explain this schematic on the top right-hand side too much. I think we've all learned and lived with the consequences of Denard's and Moore's not going any further or dying a gentle, slow death. We know we've spent a lot of time, energy, and resources in upgrading our scientific codes to deal with the end of Denard's and Moore's law. If you think about the total cost of scientific codes and how much it takes to continue to be able to extract the performance with every next generation that comes, again, as a consequence of the end of Denard's and Moore, I think it's true, and many people will agree, that it's unsustainable trying to keep moving scientific codes up. And so one way to think about it is, okay, you get the performance that you get from your single task, and task here is the same as an executable unit. But now let's start thinking about the application as a whole, the workflow as a whole, and importantly, think beyond single task performance. So you're no longer limited by the immediate implications of this. And some of you heard Jack at his Turing Award lecture last year talk about there's plenty of room at the top, which was a riff on Feynman's there's plenty of room at the bottom. So a riff on Jack is there's plenty of room on the side. There's even more room on the side, I would like to say. So now you've got plenty of tasks that you can run, and that's one way of thinking about performance. So not optimizing for single task performance, but now optimizing for multitask performance. So that's one important trend. But the other trend from the applications point of view, and seeing many application scientists in the audience, I think it is also important to appreciate that the way scientific applications are being developed has been changing. More and more applications are assembled, multiple components, into these higher level patterns, motifs, ensembles, stirred ensembles, so on and so forth. And these, if you will, higher level patterns can be arbitrarily complex. Sometimes there are multiple stages, pipelines, so on and so forth, and multiple hierarchies of parallelism. An example I'll get into very soon is you can have pipelines. You can have multiple pipelines, ensembles of pipelines. Each of these pipelines is a stage, each has multiple stages, and each of these stages is a workflow. So you've got a coupling of workflows, and inside each of these workflows, you can have a large number of ensembles, different ensembles for different workflows, and they all progress at different rates. So conceptually similar to maybe a simple bag of tasks, but I hope you see the multiple hierarchical nature of the structure of this application, and trying to execute these at scale remains a non-trivial challenge. We're just stepping away from the specific schematic here. The important point is more and more applications, campaigns are composed of components, and each of these components is obviously high performant, but the whole application entity is also a very high performant application, number one. Number two, and these are not, I repeat, these are not embarrassingly parallel applications, because there's a fair amount of coupling between the units. Okay, so as I said, workflows mean many different things to many different people, so I just want to give three illustrative examples, and then I'll try to draw some generalizing, if you will, take-home messages. So at least when we go to the next stage, thinking about the implications of workflows, we at least share some of the common features as part of our mental model. Okay, so step back. We talk about post-ECP, post-exascale. We hopefully are living in a post-COVID world, but during the COVID era, 2020, the US government, and in particular the Department of Energy I represent currently, was tasked with helping the government, the US government, create a response at multiple levels, everything from trying to help improve manufacturing to epidemiological predictions, to helping design in partnership with the private sector, obviously, targeted therapeutics. And this particular bullet point is what I will talk about in the context of what became known as the National Virtual Biotechnology Laboratory. And the whole idea of the bullet point supercomputing was to try to see how HPC and AI put together could advance the design of drugs and eventually also vaccines, but I won't talk about that now. So to give you the upshot, 100 billion candidates, these are the drug-like candidates, some of which are completely bogus, but some of which are potentially promising. And so to give you a number, again, you'll have to kind of take at face value that the number of 100 billion candidates is a very, very large number, arguably some of the largest, if not the largest number of candidates screened from, let's say, at the very early stages, what we call docking calculations at the very top, cheap and cheerful, to almost quantum computation calculations at the bottom. And the important point is every stage is more computationally intensive, but it's also much more accurate. And so the gold standard is if you can do the binding free energies down here, but you obviously can't do binding free energy calculations for all the drug candidates, the 100 billion. So you need some progressive filtering approach so that you employ only for the most promising drug candidates, the expensive gold standards binding free energy, right? So that's the overall campaign. Just to put this into context without getting into the details, what's the scale of the operation that we performed? So maybe I should do this in the reverse order. I want you to see the 2.5 into 10 to the power 6, 2.5 million node hours. That's about 2 times, 3 times the size of a traditional Insight Award in the US, which probably is worth somewhere a few $1 million of compute time. And so this is a couple of Insight Awards, and all of this was performed within a few months to get the drug candidate we came through. And just to give you a sense of the peak performance, we obviously ran full scale on Summit, which was the #1 supercomputer at that time, but also a very different machine at NSF, at TAC, an NSF machine called Frontera, which had no GPUs, right? And so you hopefully get a sense that these were real, very intensive calculations, full machine. And importantly, probably the most important point is there was no single calculation type. There were very simple function calls, docking calculations, to very expensive binding free energy calculations, to something in between, which was ML-driven, machine learning-driven, molecular dynamics enhanced sampling, right? And the fact that we were able to do 100 billion, take it all the way from the top to the bottom stages, is a consequence of two things. One is obviously being able to run on the largest supercomputers at that time, fine. But importantly, the fact that the methodological advances at each of these levels allowed us, and in particular, coupling AI methods to traditional HPC methods, allowed us to improve the overall efficiency of our throughput, of our calculations, right? So more on that later. Let me give you a second example, and this example hopefully resonates with many of you, because this is in principle an ensemble-based calculation, but it is very different from a traditional bag of tasks, because what you have is a pipeline of different, so here you see the pipeline, 3 different calculations. Each of them in turn is an MPI-based calculation, and each stage of the pipeline, stage 3, stage 2, stage 1, has an ensemble, but there are different ensembles in each stage. And these pipes, if you will, pipelines, there are a large number of them running concurrently, but asynchronously. And so you have this hierarchical parallelism, and all I want to show you here is you have a bunch of heterogeneous tasks with some constraints on them, so not constraints in the order in which they can run, so not your trivial bag of tasks. And on Frontier, which is the latest and greatest machine in the DOE system, what you see is a full machine, approximately 8,000 nodes, some nodes reserved for service capabilities here, all GPUs, all CPUs being utilized to run this over several hours. Maybe this is just a bit more than 2.5 hours. And the graph at the bottom tells you that the bag of tasks, to use that term slightly loosely, you have about 8,000 tasks, and at any given instant of time, you're running somewhere around 1,000, and you're maintaining that constant pressure of 1,000 tasks, right? So this is just to tell you that generalized notion of a ensemble based, but in a very different way, in the sense there's multiple ensembles at multiple levels. So the key idea here is hierarchical parallelism, okay? And then the third category of workflows, just want to, as part of the level setting, is where you're continuing to do high performance computing on the supercomputers, but now you are actually coupling experimental data. It doesn't always have to be real time. It may be real time, it may be near real time, it may be even lag. But the important point is your simulations, your traditional workflows on the HPC are aware of external data, and the external data is being used to drive the simulations, the workflows. And there's a lot to say here. This is something that's occupying the DOE significantly. Monday, Tuesday, and Wednesday of this week, several of our colleagues were in DC. I was there Monday, Tuesday, really thinking about how to build up the infrastructure for what is being called the integrated research infrastructure. And again, many details here, but just to try to give you an example that within this very large class of applications. You can see there are 28 facilities, probably 18 represented here in these small boxes, everything from light sources to atmospheric radiation measurements, so on and so forth. So what are generally called experimental and observational user facilities, data sources, and through a careful analysis of 72 use cases, that's what the meta-analysis, the kind of distillation of these 72 use cases into 3 primary patterns, what are called time-sensitive, data integration and intensive patterns, and then long-term campaign patterns. Think high-energy physics, where you've got to run a campaign to analyze the data over months, years, so on and so forth. And the only point I want you to appreciate here is that these patterns cross scientific domains, and the graph on the top right-hand corner is just showing you different offices, different programs, pardon the DOE speak here, but everything from biological and environmental sciences to basic energy sciences to high-energy physics. They all have analyzed these 72 workflows that they support from the light sources, from the experimental and observational facilities, and they have kind of got different, if you will, distributions across the 3 classes. Okay, so there's many more types of workflows. I've obviously given you a biased sample selection of them, but hopefully at this stage we all appreciate when we think of workflows that there are at least 3 types: the high throughput of high performance tasks, the ensemble based. There's the distributed federated data integrated with simulations. There's the AI coupled. I haven't given you details, I'll spend some time on that, but stop not just doing traditional vanilla HPC, but AI in the mix. And there are many others, right? So these are just 3 classes. But importantly, I hope we all appreciate that for a given workflow or across different workflows, the unit of execution, the tasks, can be very different. So you can have a very large range of granularity and performance requirements. You can have single cores, single nodes, multi-nodes, function calls, and so these workflows have to manage a large set in terms of diversity of tasks. And these tasks obviously in turn encapsulate different programming and computing models. So the perspective I'd like to kind of leave you with at this point in the talk is, in many ways, workflows are the highest level of execution, parallelism, and programming. And trying to think about the programming aspects, thinking about how you develop them, requires a fair amount of changes in the way we've thought of applications traditionally, right? Because of the simple reason that you've got this hierarchy of communication, coordination, and, if you will, parallelism. And interestingly, the challenge of reasoning about performance, where the performance bottlenecks are, what is the barrier to performance, is a very different ballpark, very different style of reasoning and thinking about the system and the application than traditional HPC. So again, without getting into too much of details of the applications, I hope you're with me when I say that workflows require us to rethink some of these very near and dear, very important intrinsic aspects about high performance computing. Okay, so whereas I'm going to then obviously talk about the implications, if you will, of these, I want to take a small interlude and spend maybe 5 to 10 minutes talking about my favorite class of workflows. And you'll see why I think why hopefully it resonates with many of you. So again, just let's remember the implications of that, and to right? And so the idea here is to make it easier for you to use different components that they work on these systems. And the fact that this is open, there's a well-defined policy, well-defined approach for you to contribute to this workflow system, workflow SDK, whilst leveraging the existing capabilities. Now, just closing out very quickly with the fact that even as a lot of the underlying, if you will, components change, what we've managed to do is at least start converging on the interfaces. And just one example is what is called SIJ, the Portable Submission Interface for Jobs. It shows you a kind of a well-defined, community-driven, but an interface for these most common batch queue systems, which are then again utilized on a set of different supercomputers. So again, just to give you an example of what the advantages of the Workflows SDK, not only does it help you bring in new ideas, new advances in the workflow regime, but it allows you to leverage existing components that then give you a lot of the challenges, that address many of the existing challenges and barriers to utilizing HPC systems for workflows. Okay, so just to summarize, close out, I hope I've convinced you workflows are increasingly important for scientific discovery. Both the technology trend and the application requirements mandate this. Workflows are truly the highest level of execution and parallelism, but workflows require a fundamental rethink of how we think about performance in this regime, and importantly forces us to think about collective performance as opposed to single task performance. And if indeed workflow systems are going to be privileged, I think we're seeing some of the most significant changes in the supercomputing software ecosystem in at least in a generation to be ready to support workflows as the first class entities that they ought to be. Thank you very much for your attention.
Thank you, Senator. We have about 5 minutes for questions.
Please. Please. Yeah.
Thank you very much. That was really interesting. When you look at multi-stage workflows, they often result in these sort of serialization points with the data. It goes out to the file system and one stage completes and the next one starts. Is there anything going on to optimize that so that we can place new tasks that follow on from previous tasks in a more intelligent way?
Absolutely. It's not something I do myself, but I know many colleagues that are trying to optimize that. One of the optimizations, don't write to disk if you can, and there are tools and approaches for that. But then if you have to write to disk because of volumes or because there's some uncertainty in which tasks need them when, then obviously trying to think carefully about data placement and data I/O. So a lot of these workflows use Darshan. You probably know that very well, to start understanding the I/O patterns, properties, and then there's It's still very manual, so that's the upshot. And I'm seeing more and more tools come up that try to improve that. Just one shameless plug from a colleague of mine, TaskVine. It's something that literally just is making its introduction at supercomputing that addresses some of these problems. There are many more that are needed. Yeah, thank you. Sarah.
Thanks for the fabulous talk. So we're obviously designing our new exascale systems, and for biological stuff we need these coupled multi-physics workflows. What advice do you have for us on designing our new exascale hardware for taking this sort of thing into account?
So I know very little about hardware. So I really the best thing I can say about hardware is don't listen to me, right? I spent the better part of my last few decades thinking about the software, and be glad to tell you and start thinking about this building blocks approach and why thinking about the software ecosystem is something we could do together, but is really valuable, especially for the kinds of problems I know you're interested in.
Mark has a question.
Mark.
So yeah, very interesting talk, thank you. You talk about workflows being privileged as kind of first-class applications. Do you see it in that list you had from, I think it was Oak Ridge, there were kind of monolithic codes as well as workflows. Do you see workflows replacing monolithic codes, or do we recast monolithic calculations as a type of workflow? Or
I think there'll be coexistence, because ultimately the workflow is bringing together these monolithic applications, the LAMPs, the QCD, and so on. So I would never want to say that workflow should replace them. They should be this higher level consideration, a hierarchy, if you again, of benchmarks. So you've got to have the NAMDs and the LAMPs and the NWChems work very well, and then it makes sense to think about how you marshal, coordinate, and bring them together. So that's my view. I hope I've understood your question.
Yeah, last one.
So, regarding the different workflows, and you rightly point out there are 1 billion and one workflows.
Yeah.
Why create 1 billion and second one rather than just trying to work with somebody like Galaxy or Swift or one of the other workflows to try and optimize as many of those for HPC usage?
Yeah.
So we still have this wide ecosystem.
So I'm sorry I conveyed the impression. We're not developing a workflow to replace but I mean, it's a proverbial, the 15th standard to replace every, so you know the jokes there. Absolutely not. ExoWorks SDK is not replacing. It is creating the policy, the interfaces, and an overall infrastructure that you can continue to use your workflow system, but then in conjunction. So that's the first thing. It's trying to create policies, deployment, and interfaces. And I didn't have time to give you examples, but instead of taking, let's say, Galaxy and assuming Galaxy can do everything end to end, what would you need to do if there were certain parts of, let's say, Galaxy that weren't optimal for an exascale machine? Could you swap in a component that existed that had been super optimized for Frontier? And so that's what the SDK does. Now, having said that, I also did mention that the bulk of the workflow systems, of the 1 billion and one, all but 4 have origins outside of HPC for use cases such as Galaxy. There are only 2 or 3 workflows that have fundamentally thought of HPC platforms and HPC performance as a first-class consideration. You'll pardon the bias here, but those were the 3 or 4 that got together to form the first 3 and 4 components in the ExoWorks SDK. But importantly, now that we've worked together, for example, there's Radical, which I've developed, along with Parcel coming out of Ian Foster's team. So these can work together on a large number of different use cases, along with something coming out of Livermore called Flux. So there are things that Flux can't do everything. There are scenarios where Radical can't do everything. There are scenarios where Parcel can't do everything. The fact that you can now use these interchangeably is a first in the state of the art for sure. Secondly, having done that, we're extending this to any of the other tools that you mentioned and making it easier.
Thank you, Shantenu.
Thank you.